Welcome to the second part of Lecture 15, the Laplacian. It's titled The Electric Field and Laplace's Equation. So the electric field is probably one of the most important applications of vector calculus into the field of physics. So we want to try and apply some of the previous methods to the static electric field. Now you may or may not have seen this particular form of Maxwell's equations. It's called the differential form of Maxwell's equations, but they say that the curl of E is equal to 0 and the divergence of E is equal to the charge density divided by epsilon naught. Now since the curl vanishes, that implies that we can write the electric field as the gradient of some scalar. We pick that scalar to be minus phi. So we write the electric field E equals minus gradient of phi, and the reason why the minus sign is chosen is primarily a convention, but it implies that high potentials are regions where electrons like to be and low potentials are regions where electrons don't like to be. Hence, the divergence of the gradient of psi, which is an object that we call del squared of phi, is equal to minus the charge density divided by epsilon naught, and that's called Poisson's equation. So we got to figure out what is del squared. Well, it's equal to the dot product of the gradient with itself, and since the gradient is d by dx times I hat plus d by dy times j hat plus d by dz times k hat, when I take del dot that, I get for the x component the second derivative with respect to x squared, for the y component the second derivative with respect to y squared, and for the z component the second derivative with respect to z squared. And so it just becomes d squared by dx squared plus d squared by dy squared plus d squared by dz squared. Now note, this is the form in Cartesian coordinates. If we go to cylindrical or we go to spherical coordinates, the form of the Laplacian does change, and you're going to see an example of that fairly shortly during this lecture itself. Now it turns out in most electrostatics problems we actually don't set charges anywhere. What we do is we set potentials on surfaces, and so what we want to do is we want to solve this equation but in free space with the boundary conditions, and then the equation becomes del squared phi is equal to 0. That's called Laplace's equation, and we have to supplement that equation with some appropriate boundary conditions, which usually are given by the values of the potentials on different metal surfaces. And this sounds like a lot, sounds very complicated. It's easiest to see how this works by looking at some examples. The picture on the left-hand side is the picture of a voltage profile that we're going to be looking at a little bit later in the class. In just a couple of lectures, we'll be looking at something that has exactly that form for its solution. All right, the first example we want to look at are infinite planar planes of charge, which we'd call an infinite planar capacitor. And the question is, what is the electric field between two infinite parallel metal planes that are separated by a distance d and have a voltage of 0 on the left plane and a voltage of V on the right plane? So we imagine that we attach these planes to a battery so that we get a voltage difference across them, and the question is, what is the electric field? Because the planes are infinite, that means that, and we're going to take them in the YZ direction so that the separation is in the X direction. Because they're infinite, that means that the voltage can only depend on the coordinate X. You should be able to convince yourself that if I have an infinite plane, I can't tell what one position on the plane is relative to another position on the plane. So there can't be any Y or Z dependence to anything. And so what that means is that the electric field is going to end up pointing in the X direction only. And so the field lines which are drawn in the figure are parallel to the X-axis as they're drawn in that figure. So because phi only depends on x, our Laplace's equation simply becomes the second derivative of phi with respect to x squared is equal to 0. That's a very easy differential equation to solve. It simply says phi is equal to ax plus b, a linear function. Now we use the boundary conditions to determine a and b. So we know phi of 0 is equal to 0. Let's set the coordinate 0 at the left-hand plane. That means b is equal to 0. We furthermore know phi of d is equal to v. That means A has to equal v divided by d. So our potential phi is equal to Vx over d. This is a linear function. The electric field is minus the gradient of that, and so the electric field is just minus v over d in the x direction, 0, 0. So as we said before, there'll be no component along the y or the z direction, and so we get this electric field is minus v over d. All right, we solved our first example of Laplace's equation. Let's take a look at a second example. Here we're going to look at a spherical capacitor. We have a spherical shell on the outside, and we have a sphere on the inside. They're both made out of metal. The inner sphere has a radius r1. The outer sphere has a radius r2. And the question we want to ask is, what is the electric field between the two metal spheres when we have a voltage of 0 on the outer sphere and a voltage of V on the inner sphere? So it's best to work in spherical coordinates for a problem that involves a sphere, and now we have to work out what is the Laplacian in spherical coordinates. It turns out that Laplacian is 1 over r squared d by dr of r squared d phi by dr plus 1 over r squared sine theta d by d theta of the quantity sine theta d phi by d theta plus 1 over r squared sine squared theta d squared phi d phi squared. Now remember, we have spherical symmetry here. So because we have spherical symmetry, in this case, there should be no theta or phi dependence to our result. So the second two terms in this Laplacian are going to go away, and we're going to just be left with the first term. And our Laplace's equation is simply going to be 1 over r squared d by dr, r squared d phi by dr is equal to 0. Now I can take that, I can get rid of the 1 over r squared, and because when the derivative of something is equal to 0, that means the something is a constant. What we learn is r squared d phi by dr is equal to a constant. Now if I divide by r squared, that tells me d phi by dr is equal to a constant over r squared. I need to integrate that, and I find phi is equal to minus c over r plus another constant. Okay, just like before, onto our boundary conditions. Phi evaluated at the outer radius, r2, is equal to 0. That tells us c prime is equal to c over r2. Phi of r1 is equal to v. You need to work out this algebra. It's just a couple of lines to find that c is equal to r1 r2 over r1 minus r2 times v. We put this together and we find phi of r is equal to r1 over r2 minus r1v multiplied by r2 over r minus 1. To find the radial component of E, I have to take the gradient in spherical coordinates, and that gradient ends up being just the derivative with respect to r in the r hat direction. And so I get r1 r2 over r2 minus r1 times v over r squared. The theta and phi components, because there's no theta or phi dependence to phi of r, are both equal to 0. And so the electric field vanishes on in those two directions. So we just have a radial electric field, as we suspected we would, and it decays like 1 over r squared with some particular constants as we move outward. Okay, we've now solved our second Laplace's equation, and that concludes lecture 15.